Okay, so today is going to be our final lecture in preparation for test 2, which is actually going to be 1 week from today. And today our last lecture for the chapter or the unit on bonding is going to involve calculations, and these are going to be calculations for determining empirical formulas of compounds and molecular formulas. So an empirical formula is actually the simplest whole number ratio of the atoms of different elements in the formula of a compound. The simplest whole number ratio of the atoms of different elements in a particular compound. Now, when you draw the Lewis structure of a covalent compound, you're showing all the atoms that are bonded together to make up a unit called a molecule. When you draw a Lewis structure of an ionic compound, you're not showing all the ions in a crystal of an ionic compound. You're showing the simplest ratio between the ions. So ionic compounds are always represented by empirical formulas, but covalent compounds usually aren't. They're represented by what we call molecular formulas, and a molecular formula actually tells the number of atoms that are bonded together to make a particular molecule. So we talked about this particular molecule a couple of days ago, or yeah, actually yesterday, I think. Do you know what the name of this molecule is, C6H6?
Benzene.
That's benzene. The reason it's written like that is if you draw the Lewis structure, there's 12 atoms that bond together to make that particular molecule. That's its molecular formula. And usually we represent benzene as C6H6. But if there was some reason you wanted to represent the simplest whole number ratio of the atoms in the compound, then what you would do is you would recognize both the C and the H atoms are divisible by 6, divide them both by 6, and you would get the simplest ratio between carbon and hydrogen is 1:1. That would be an empirical formula, okay? This is the molecular formula for the covalently bonded substance glucose, C6H12O6. There are 24 atoms that bond together to make a glucose molecule. That's why that's the molecular formula. If you wanted to represent the simplest ratio between the different elements, you divide all those by 6, and the empirical formula would be C1H2O1. This is water. What would be the empirical formula for water? What would that be?
H2O. Doesn't have one.
Sometimes a molecular formula is an empirical formula. It's the simplest ratio, okay? So when we have ionic compounds, they're always given as empirical formulas. When you have covalent compounds, the most relevant thing to know about them is what's their molecular formula. But it turns out there is an experimental way to determine the empirical formula. So that's why we're even talking about these. And we're going to talk about how you can take experimental data and determine the empirical formula of either an ionic or covalent compound. And then at the end of today, we're going to see if we have one extra bit of information, we can actually go from the empirical formula to the molecular formula, and we'll actually know how many atoms bond together to make one molecule of each of the different substances. So here's an example from experimental data. We're going to try to find the empirical formula of a compound that is 75.0% carbon and 25.0% hydrogen by mass. Now, where do these numbers come from? Let's say you take a compound between carbon and hydrogen, and let's say the sample and lab you're dealing with, you weighed it on your excellent balance that never has any fluctuations in it, and it comes out 4 grams. And then you decompose it, and you find out of the 4 grams, 3 grams is carbon and 1 gram is hydrogen. Well, carbon is 3 out of 4. That's 75%. Hydrogen is 1 out of 4. That's 25%. So this would be the type of mass data you would get from an experiment if you decompose the compound. So the question is, if you know what its percentages of carbon and what its percentages of hydrogen by mass, can you determine its empirical formula? And the answer is yes. Now, to do an empirical formula determination, you actually have to start with mass data. If they would have just told me we decomposed the sample and it was 3 grams of carbon and 1 gram of hydrogen, that's perfect. I'm going to start my calculation with 3 grams and 1 gram. But if they don't tell you actual masses, but they tell you percentages by masses, you're going to have to start by making an assumption. And you're going to have to just assume you have a fictitious 100 grams of the compound. Because if you do, that means that out of the 100 grams, I guess 75 grams were carbon and 25 grams were hydrogen. So by assuming a fictitious amount of 100, whatever the percents are, those can now become the masses of the individual elements making up the compound. So actually, you're going to do a calculation with this fake sample that's 75 grams of carbon and 25 grams of hydrogen. but the answer is going to come out exactly the same as if you would have started with 3 grams of carbon and 1 gram of hydrogen, if that's what they weighed in the experiment. So once you determine the masses of the elements making up the compound, the second thing you're going to have to do is you have to calculate the number of moles of each element, and in specific, the moles of atoms of each element. And I'm only saying that because I don't want you to take into account that hydrogen is a diatomic element, so maybe you should try to figure out how many moles of diatomic hydrogen are in the formula of the compound. An empirical formula is the simplest ratio of the atoms of the different elements in a compound that make it up. And so we're going to want to calculate the moles of atoms of each element. So whether something in its natural state is diatomic like hydrogen, or maybe octaatomic like sulfur, we don't take that into account when you're doing an empirical formula determination. So how do we get moles? This was on our first test. Let's go way back then. If you have 75.0 grams of carbon in this fictitious sample, you go to the periodic table, look at the block for carbon, it says 12.01. What does that mean? On the microscopic scale, it means 12.01 AMUs equals the mass of one average carbon atom, but we're not using that. On the macroscopic scale, it means if you weigh out 12.01 grams of carbon, that will equal a mole of carbon atoms. So that equality statement can be written 12.01 grams of carbon equals 1 mole of carbon atoms. I write that as a fraction, and I arrange it so the grams will cancel out by putting the 12.01 grams of carbon on the bottom and putting 1 mole of carbon on the top, because I just wrote a C there. That really means 1 mole of carbon atoms, but they hardly ever write that. They just write 1 mole of carbon. And when they write a C, that means elemental carbon. So if we calculate this out, this should be a 3 significant figured number because of the 75.0, but I'm not at the end of my calculation yet, so I'm going to keep a guard digit, and that green 5 is the guard digit, so 6.245 moles of carbon. We'll do the same thing with the hydrogen. We'll take the 25.0 grams of hydrogen, look up hydrogen's molar mass on the periodic table, and it says 1.01. That means 1.01 grams of hydrogen equals 1 mole of hydrogen atoms. Make that into a fraction, put the gram part of that on the bottom, 1.01 grams of hydrogen on the bottom, mole on the top, grams cancel out, and the 3 significant figures, 24.7 with a guard digit 5 moles of hydrogen. So this is actually really relevant now. Once you've now calculated how many moles of the different elements are in this sample, whatever the mole ratio is has to be the atom ratio, because moles are proportional to atoms, right? If somebody has 3 dozen eggs and somebody has 6 dozen eggs, that's a 3 to 6 or 1 to 2 ratio. Well, the ratio of eggs is going to be the same as the ratio of dozens. So the ratio of moles has to be the same as the ratio of atoms. So if you can look at 6.245 and 24.75, and I go, I wonder what the simplest ratio is between those, that's going to be the empirical formula, because that'll be the simplest atom ratio. But if you look at those two numbers and go, wow, those are decimals, I don't know what the simplest ratio is. Well, here's how you actually can do it to get the right answer for sure. You take your number of moles and divide each number of moles by whichever one is the smallest number. And out of the two values, 6.245 moles of carbon and 24.75 moles of hydrogen, the 6.245 is smallest. So take the number of moles of each element, divide them by the smallest number, and you're going to get some integer. For the carbon one, it's going to be 1.00, because that's 6.245 divided by 6.245. When we do the hydrogen, what do we get? We get 3.96. So this is saying this sample is 1 mole of carbon to 3.96 moles of hydrogen. And that 3.96 is really, really close to the integer 4. So it's probably really saying that it's 1 mole of carbon to 4 moles of hydrogen. And if the mole ratio is 1 to 4, the atom ratio will be 1 to 4. So the integer mole ratio must also be the atom ratio. You assume the formula is CH4.
So, Professor, when do we know to use diatomic hydrogen in empirical formulas
You'll
then?
never use that in an empirical formula determination, because nobody ever wants to know how many diatomic molecules are in the formula of a compound. They always want to know how many atoms there are. So empirical formula determinations, never. When we start doing chemical reactions and we say carbon is reacting with hydrogen gas, well, what's hydrogen gas? That's diatomic. That's when that'll be used. Does that make sense? Now, how come this number here came out 3.96 and it didn't come out 4.00?
We have have like rounded numbers? It's not the exact number?
Well, remember where this came from. This is experimental data, correct?
Yeah.
So how does your experimental data always work out in labs? When you were doing your 5 milliliters of water last week in experiment 2 and you did it 3 times in a row, did you get the same number every single time?
No.
Oh no, experimental error by you. So this is probably some experimental error. So you'll have to accept a little bit of variance. So what can we accept? We usually go by the fact that if the number you get here is within 1/10 of a mole of an integer, you can assume that 1/10 too high or too low is experimental error, and you can round it to the nearest integer. So that number could have been 3.90 as its lowest, 4.10 as its highest, and that would be within 1/10 of the integer 4, and we can assume that's experimental error. Does that make sense? This one's clearly within that range, so that's why I can assume this ratio was a 1-to-4 ratio. Okay? Now, let's try another one, and we'll watch what happens here at the end of this problem. We're going to find the empirical formula of a compound that is 90.0% carbon and 10.0% hydrogen by mass. So exact same thing as the last problem. We're given experimental data, which there may be some experimental error, okay? And so we need to calculate the empirical formula by first starting with masses of the 2 different elements. And if somebody would have said, oh, in the experiment, it was 8.137 grams of carbon and 1.026 grams of hydrogen, perfect. You take those 2 masses, and then what do we do with those? We convert them into moles. But we weren't given masses, so we have to do the first step, and we have to make an assumption that there's a fictitious 100 grams of the compound. So if it is, that means this must be 90.0 grams of carbon and 10.0 grams of hydrogen. So first step, assume 100 grams of the compound if you're not given mass data, and that will allow you, therefore, to come up with your own mass data, 90.0 grams of carbon, 10.0 grams of hydrogen. Now, once you have mass data, we always have to convert this into something that's proportional to the atoms, and that's moles. So we're going to convert the 90 grams of carbon into moles, the 10 grams of hydrogen into moles, and we do that with the molar mass. And we just saw that in the last problem, so this is not going to be anything earth-shatteringly new. So if we take the molar mass of carbon and invert it so the grams will cancel out, 90 multiplied by 1 divided by 12.01, that's going to give me the number of moles of carbon in this fictitious sample. Answer should be 3 significant figures. I'm going to keep a guard digit. We take the 10.0 grams of hydrogen, use its molar mass from the periodic table, arrange it so the grams will cancel out. We'll now calculate how many moles of hydrogen are in this fictitious sample. 3 significant figures, and then we're not at the end of the calculation, so I'm going to keep a guard digit. So we calculate the moles of the 2 different elements. 7.494 to 9.901. There's got to be some integer ratio there, but looking at those, I would go, I don't know what it is. So the for sure way to do that is to take the number of moles of each of the elements, divide them by the smallest number. And as you recall from elementary school, 7 is smaller than 9, right? So divide both of these by 7.494. Whenever you do this, you're always going to get 1 mole for whichever element had the smaller number of moles. That's what's going to happen for the carbon here. We're going to get 1.00 moles of carbon, and then you have to divide the hydrogen numbers, 9.901 by 7.494, and when you do that, you get 1.321 moles of hydrogen. Okay, so this says 1 mole of carbon to 1.32 moles of hydrogen. Is this, do you think, close enough to an integer to assume this is just some experimental error?
No.
No, probably not. I don't know, maybe Mr. Peck would go, yeah, that's probably right, because my error is usually about that big. But I mean, in reality, most of the time, no. That's greater than 0.1 away from the integer 1. If this was anywhere from 0.90 up to 1.10, we can assume it's a 1-to-1 ratio. But that's 1.32 is too far away, so it's not a number that we can round to 1. So here's what you do. You take both numbers, you've got to keep the ratio the same, 1 to 1.32. You try multiplying them by successive numbers. The first number you try is multiplying by 2. So if the moles of all elements are not within 0.1 moles of an integer, they all must be multiplied by an integer until you make them integers. And so the first thing we're going to try is we're going to try to multiply both of those by 2. So when we multiply both of those by 2, the carbon one you can do in your head. 1.000 times 2 is 2.000. The 1.321 times 2, if you work that out, comes out to be 2.64. Now, this is within an integer. Lovely. Is this within a tenth of an integer?
No, not yet.
It would have had to be like 2.90 up to 3.10 if you were going to assume you're going to round that to 3. So you know what? This didn't work. Erase it. That was all wrong. So if multiply by 2 doesn't work, the next thing you do is you try multiplying by 3. So we'll try multiplying both by 3, and we'll see if this winds up making integers. 1.000 times 3 is 3, and then 1.321 times 3 turns out to be 3.96, and that is within that magical range of 0.1 of an integer. It's between 3.90 and 4.10. So that means now we can round that number of moles of hydrogen to the integer 4. And so this sample really probably was, without experimental error, 3 moles of carbon to 4 moles of hydrogen. And if the mole ratio is 3 to 4, the atom ratio must be 3 to 4. So we would say the empirical formula is C3H4. That makes sense how you handle something like that? If multiplying by 3 did not make the second number an integer, you erase that, you multiply by 4. If that doesn't work, you erase that, you multiply by 5. You keep doing it until you actually get the right answer. Now, for those of you that are good at fractions and decimal equivalents, you could have predicted you would have needed to multiply by 3 and not even tried multiplying by 2 by looking at the number over here. What did we get? 1.32 was the first number we got. What is that close to in terms of decimals? 1.32, oh, that is a decimal. What's it close to in fractions? 1.32 is really close to 1 1/3, because 1 1/3 would be 1.33, right? So if you recognize that your second value is close to a fraction whose denominator is 3, 1 1/3, that's how you know to multiply by 3. So if you're good at the fraction decimal equivalents, you can predict what you need to multiply by. But if you aren't, then you multiply by 2 and see if it works. If it doesn't, erase it. Multiply by 3, see if it works. If it doesn't, erase it. And you keep going until you wind up getting both numbers within a tenth of a mole of an integer. Okay? So those are empirical formula determinations where you determine the formula of the compound, at least its empirical formula, from experimental data. Now, something else about compounds, we've been talking about how covalent ionic compounds are bonded together this whole unit. I want to talk about a property of a compound called its molar mass. We already know what the molar mass of an element is. That's just how many grams you need to weigh out in a balance to equal 1 mole of atoms of that element. Well, you can do the same thing for a compound. What if you have salt, for example? The question would be, how much salt do I have to put on a balance to make sure I have 1 mole of sodium chloride formula units? So whatever that is, that's called the compound's molar mass. It's the mass of 1 mole of molecules, if it's a molecular substance, or 1 mole of formula units, if it's an ionic substance. So we're going to show you how to calculate the molar mass of a compound, the mass of 1 mole of molecules, if it's a molecular or covalent substance, or 1 mole of formula units, they're called the empirical formula. The formula units are called empirical formula, or empirical formulas of ionic compounds are called formula units for an ionic substance. What's the name of this compound?
Aluminum 3 sulfate.
Aluminum always forms positive 3 ions, therefore the 3 will not be necessary in the name. So you just call the first ion aluminum, the second ion is sulfate. This is just aluminum sulfate. So if you want to calculate how many grams of aluminum sulfate you would have to weigh out on a balance to make sure you had a mole, or 6.022 times 10 to the 23rd formula units of this compound, which is its molar mass, we're going to do it by breaking it apart into its constituent elements. This particular formula has 2 aluminums in it. Is that correct? You can look up on the periodic table and you can figure out what the mass of 1 mole of aluminum is. So if this formula has 2 aluminums in it, that means 1 mole of this compound would contain 2 moles of aluminum. And to get the mass of 2 moles of aluminum, I'm going to go 2 multiplied by whatever the molar mass of aluminum is on the periodic table. So for 1 mole of the compound, it contains 2 moles of aluminum. So I go 2 moles of aluminum multiplied by its molar mass from the periodic table, which is 26.98 grams per mole. And that'll give me 53.96 grams. The next component, the next elemental component here is sulfur. And if we have 1 mole of this compound, how many moles of sulfur are there? It looks like 1 right now, but see there's a 3 on the outside of the parentheses. So if you distribute that, that would be 3 moles of sulfur. So 1 mole of aluminum sulfate contains 3 moles of sulfur. What's the mass of 3 moles of sulfur? It's 3 moles multiplied by whatever the molar mass of sulfur is from the periodic table, which is 32.07 grams per mole. And then finally, there's only one other elemental component of this particular compound, that's oxygen. And we have a 4 inside the parentheses and a 3 outside, so we have to multiply them. So 1 mole of this compound contains 12 moles of oxygen. And to get the mass of 12 moles of oxygen, we go 12 moles multiplied by oxygen's molar mass, which is 16.00. In this case, just watching the significant figures, something kind of funky happens here. When you go 12 times 16.00, you're going to get a 4 significant figure number. And the answer I get is 192.0, which means the answer is only accurate to the 10th place now. So when you're going to add these up, that last column, the 6 plus the 7 plus the guard digit, turns out to be a guard digit 7. So you're going to actually have to round your answer back to the 10th place. So this comes out, rounded to the right number of significant figures, 342.2 grams. You have calculated how many grams of aluminum sulfate you have to weigh out on a balance to ensure that you have 1 mole of aluminum sulfate formula units. 6.022 times 10 to the 23rd aluminum sulfate formula units. So that's the mass necessary to have 1 mole of the aluminum sulfate formula units. This is its molar mass. You could write an equality statement for that. 342.2 grams of aluminum sulfate equals 1 mole of aluminum sulfate, completely analogous to what you do for elements from the periodic table. We can do the same thing for compounds, okay? If that makes sense to you, we're going to give you one to calculate the molar mass for. So I want you to take a minute and a half and see if you can calculate the molar mass of carbon tetrachloride. And then in a minute and a half, we'll come back and we'll see if we got the answer right. You may begin. What's the formula for carbon tetrachloride?
CCl4.
Yeah. Now, this is going to be crucial on test 2. I'm not going to make you know the formulas from the names or the names from the formulas on this exam. When we get to exam 3, that's when it is going to be crucial. And there'll be things on exam 3. It'll say carbon tetrachloride and then do this 20-point calculation. And if you can't get the formula from the name or the name from the formula, that's going to be unfortunate. So we'll need to start making sure we can pass that nomenclature quiz so that we'll know names from formulas and formulas from names specifically by test 3. So if this is the actual formula of the compound, you want to know what mass you need to weigh out on a balance to give you 1 mole of carbon tetrachloride molecules. So 1 mole of carbon tetrachloride contains 1 mole of carbon. So you go 1 mole of carbon multiplied by carbon's molar mass. 1 mole of carbon tetrachloride contains 4 moles of chlorine, and to get that mass, you go 4 moles of chlorine multiplied by chlorine's molar mass, which is 35.45. And when you multiply a counted number 4 by a 4 significant figure molar mass, you get a 4 significant figure answer of 141.8. So now you recognize if you add these up, the column in the numbers in the hundredths column is going to be a guard digit because the 141.8 is only accurate to the tenths place. So you would actually say, therefore, the molar mass of carbon tetrachloride would be 153.8 grams per mole. If you wanted to have a guard digit, you can. And what's the significance of that number? And this is really why we're learning this. These numbers will be the conversion factors between grams of compounds and moles of compounds. We already know how to switch grams of an element into moles of an element. That's the element's molar mass. If you can calculate the molar mass of a compound, you can now use that to convert between grams of the compound and moles of the compound. And let's see if we can use that to do a little calculation here. We're going to try to calculate the number of chlorine atoms in 1.00 grams of carbon tetrachloride. So this particular problem is a dimensional analysis. We're starting with 1.00 grams of carbon tetrachloride, and we're trying to solve for, what is it? Chlorine atoms. So you're going to start your calculation with the given number in the problem. And sometimes you're going to need to be able to have some forward vision. What can I do with this? I've got to somehow eventually get this into atoms of chlorine. And so to start a problem, if you're ever given the mass of a compound or the mass of an element, whatever it is, we always know we can convert that into moles if we determine its molar mass. So in the top half of the slide, we calculated the molar mass of carbon tetrachloride. So I can convert the 1 gram of carbon tetrachloride into moles of carbon tetrachloride by using the 153.81 grams equals 1 mole. The 153.81 grams go on the bottom, and the 1 mole goes on the top, and the grams will cancel out, and now we'll have moles of carbon tetrachloride. And there, this is the big use for molar masses of either elements or compounds, to be able to calculate a quantity proportional to the amount of atoms or amount of molecules. Now, here's what's tricky about this one, and I want you to watch this because I want you to be able to do this. If you've now calculated how many moles of carbon tetrachloride there are, but they want moles of one of the components of carbon tetrachloride, they only want number of moles of chlorine atoms, you have to look at that formula. And just like we did on the top of the slide, we said, wow, 1 mole of carbon tetrachloride contains how much chlorine? It contains 4 moles of chlorine, right? Because that little subscript 4 right there. So there's 4 moles of chlorine in 1 mole of carbon tetrachloride. It's just like what we wrote here. There's 4 moles of chlorine in 1 mole of carbon tetrachloride. So that's an equality statement. You can say 1 mole of carbon tetrachloride equals 4 moles of chlorine. Write this now so the carbon tetrachloride cancels out by putting the 1 mole of carbon tetrachloride on the bottom and 4 moles of chlorine on the top. Cancel out carbon tetrachloride, and now we've calculated how many moles of chlorine must have been in the sample. How would that last conversion factor be different if I would have asked you how many moles of carbon are in this carbon tetrachloride sample? What would we have to do in that last conversion factor? How would it be different?
1 mole of CCl4 to 1 mole of carbon.
Right, 1 mole of CCl4 still on the bottom, but what does the formula say? There's 1 carbon in it. You put 1 mole of carbon on the top, exactly right. Okay, so this now gives you moles of chlorine. If the question says atoms of chlorine, you always switch moles into particles with Avogadro's number. If it's an atomic substance, then 1 mole of chlorine equals 6.022 times 10 to the 23rd atoms. And so I'm going to put the 1 mole of chlorine on the bottom, the 6.022 times 10 to the 23rd atoms on the top. The moles will cancel out, and we've now calculated how many atoms of chlorine must have been in the sample. Okay, first number in the whole problem is 3 significant figures. The molar mass and Avogadro's number are 4 significant figures, so the answer will get rounded to 3 significant figures, and I get 1.57 times 10 to the 22nd atoms of chlorine. Okay.
So in like water, in 1 mole of water, there's 2 moles of hydrogen and 1 mole of oxygen.
Absolutely. So you can say 1 mole of water equals 1 mole of oxygen, or 1 mole of water equals 2 moles of hydrogen. Make sense?
Yeah.
Or you can go component to component. In water, you can say 2 moles of hydrogen equals 1 mole of oxygen even. Just like for carbon tetrachloride, you could say 1 mole of carbon equals 4 moles of chlorine. All those equality statements can be determined from the formula of the compound.
Right. I just have to think about it.
Yeah. So now, once you catch on, then it makes perfect sense. You look at this, and this is either 1 atom of carbon to 4 atoms of chlorine, or on a large scale, it's 1 mole of carbon to 4 moles of chlorine. So that's got to be an equality statement. 1 mole of carbon equals 4 moles of chlorine. Stoichiometrically is how it means in terms of its equality.
Right.
Now, what if we really want to know the molecular formula of a compound? We've already seen that we can determine an empirical formula from experimental data. We're going to now try to get the molecular formula. So what's a molecular formula? We talked about it at the beginning of the period, but we didn't define it. It's the actual number of atoms of the different elements in a particular molecule. Now, we've seen experimentally how we can determine an empirical formula. Let's say we've determined the empirical formula of some compound is C1H1. And we want to know what its real molecular formula is because we want to know how many atoms are bonded together to make the molecule. Well, the molecular formula could be one of a gazillion different possibilities. The molecular formula could actually be the same as the empirical formula, C1H1. But that 1-to-1 ratio could also mean that the molecular formula is C2H2, or it could be C3H3, or it could be C4H4. And I could keep doing this forever, right? And I'm not going to. So we've got to figure out a way to go from empirical formula to molecular formula. And the way to do it is to know one thing about the particular compound in question, and that is its molar mass. Now, if you don't know its formula, you can't figure out its molar mass from the periodic table. So somehow the molar mass has to be determined experimentally. And we haven't quite reached the time in class we've learned how to do that. But in a couple of weeks, we're going to do an experiment where I'm going to hand you a bunch of white crystals. And I'm going to say at the end of the period, tell me what the molar mass is of the molecules that make up these white crystals. And in 2 hours, you're going to come back and you're going to say the molar mass is 154 grams per mole. And without even knowing what those crystals are, you're going to be able to figure it out. So you're going to have to trust me a little bit right now in that we're going to have ways eventually to calculate molar masses. But the problems I'm going to give you now at this time, I'm just going to say the molar mass was determined to be some number, and it's going to look like it just appears by magic, but it really is going to come from true experimental data. So we'll try one final problem here to show you how this works. We're going to try to find the molecular formula, so not the empirical formula, but the molecular formula of a compound that is 43.7% phosphorus and 56.3% oxygen by mass. Find the molecular formula of a compound that is 43.7% phosphorus and 56.3% oxygen by mass. And here comes the special bit of information, and has an experimentally determined molar mass of about 280 grams per mole, or for Mr. Gliozeni, of about 280 grams per mole. Mr. Gliozeni, did that make you feel more at home? Was that better?
Definitely.
Okay, good. Take off, eh?
Yeah.
Now, when you want to figure out the molecular formula of a compound, you have to do what we did at the beginning of the period first, determine its empirical formula. So I'm going to want you now to take a couple of minutes, take the 43.7% phosphorus, 56.3% oxygen, and calculate its empirical formula. We'll give you a couple minutes. And once we have the empirical formula, I will show you the one additional step you will need to do to go from empirical formula to molecular formula. You may begin. So the 3 steps to determine the empirical formula. If you're not given mass data to start, first you have to get mass data by assuming 100 grams of the compound. That's where I got 43.7 grams of phosphorus, 56.3 grams of oxygen. Second step, convert the mass into moles by dividing by their molar masses. And now we'll have the moles of the 2 different elements making up the compound. And if there were 3 elements, you would calculate moles of all 3. If there were 4 elements, you'd calculate the moles of all 4. And then the third step is divide all of the number of moles of all the different elements by whichever number is the smallest. And in this case, 1.411 is smaller than 3.519. And so this is going to come out 1.00 moles of phosphorus to 2.49 moles of oxygen. And unfortunately, the 2.49 is not close to an integer. So that means we're going to have to multiply it by something. Whatever you multiply this by, you better multiply the first one by it. Otherwise, you've messed up the ratio. So what number did you deduce you had to multiply both of these by?
2.
Yeah, 2.49 is really close to 2.5. So that the denominator is a 2. That's pretty much telling you have to multiply by 2. And if you do that, you get 2 moles of phosphorus to 4.98 moles of oxygen. And 4.98 is within 1/10 of a mole of the integer 5. So we can assume the empirical formula is P2O5. Make sense? So once you have the, say it again, sorry.
What if we took the 280 and multiplied it by the percentages?
That's an alternate way to do it, and that would work as well, okay?
Okay.
So if you now take the empirical formula P2O5 and calculate what its molar mass is, we're going to see how the molar mass of P2O5 compares to the true molar mass of 280, okay? So we're going to find the molar mass of our empirical formula and see how it compares to 280, because that's going to give us a clue as to what the true molecular formula is going to be. So calculating molar masses, we've done that earlier in the period today. For P2O5, 1 mole of P2O5 contains 2 moles of phosphorus. So it's going to be 2 moles multiplied by 30.97 grams per mole. And 1 mole of P2O5 contains 5 moles of oxygen. So we're going to go 5 moles multiplied by 16.00 grams per mole. Both these numbers accurate 2 places past the decimal point. And so when I add them up, my answer will go 2 places past the decimal point. I get 141.94. Okay. Now, if you're good conceptually, you would go, the empirical formula weighs about 140. The true molecular formula is 280. It's twice as big. How do I get a mass twice as big? I need twice the number of atoms. Multiply this by 2. But if you want a systematic way to do it, what you do is you take the actual molar mass that they had given you in the problem, 280, you divide it by the empirical formula's molar mass and see what you get. So you divide the compound's actual molar mass, that's the 280 given in the problem, by the empirical formula's molar mass, which is 141.94, and whatever you get should be very close to an integer. In fact, it should be exactly an integer, but if it isn't, it's only because of experimental error, okay? So if we take the 280 divided by the 141.94, and you do it in your calculator, this comes out 1.9 something, and it doesn't come out exactly an integer, but what is the closest integer it rounds to? 1.9 rounds to about 2. So accounting for experimental error, you can assume that the real molecule is that many times bigger than the empirical formula. So you multiply the empirical formula by 2, because this is telling you the molecular formula must be 2 times bigger than the empirical formula. And so P2O5 multiplied by 2 just means you multiply each of the subscripts by 2, and that would give you P4O10. Any questions on the molecular formula calculation?
Will we be asked to find percent error, like if we get something that's not an integer?
I guess I could have, but I'm not. That's not on the test, so no.
Okay.
You can always practice that on your own if you want, okay? So we've now finished all the material for test 2, so let me give you a list of things that you want to make sure you're preparing for over the next week. Got a couple homework assignments still to go this week on a Wednesday and Thursday now for these last couple lectures. But then next week on Monday, homework 2R will be due, and that's going to be the one where you want to make sure you can crank all your way through that and you understand everything. And any questions you have, see me, see the tutor. We'll have a review session in class on Monday next week to answer any questions you have. The test will wind up being early in the morning on Tuesday. We started the unit talking about how metals bond. That's called metallic bonding. You should know what that is. We talked about how non-metal atoms bond. They share electrons. That's called covalent bonding. And we talked about how metals and non-metals bond with each other. They form ionic bonding when they bond together. Okay. When we started talking about ionically bonded substances, we were talking about ions, and we had to give the electron configuration notations for ions. I want you to be familiar with that. So metals lose their valence electrons to form positive ions, non-metals gain electrons, and we did some examples of those. The tricky ones are the transition metals. You always have to remember you lose s electrons first, not necessarily the last ones filled, which are the Ds. So you want to make sure you get those right. We had a couple questions on the early homework assignments where I said, which one of these ions is biggest and which is smallest? So you're going to make sure you can answer questions like that. And then we spent, I think, about 5 minutes, this entire unit, on Lewis structures for ionic compounds. And I will put them on test 2. So you, when you do that on the homework 2R, make sure you pay attention. If it's a compound between a metal and a non-metal, these are made of ions. They don't share electrons. They don't draw dashes between them. You draw separate ions. So we had that early in the unit, I think homework 2A probably. And then you'll have it on homework 2R, and you'll see it on the activity 9, which is we're doing this week. Then we actually spent the other 9 lectures, so 9 hours worth, drawing Lewis structures essentially for covalent compounds. And when you draw the Lewis structure for covalent compound, if you look at a particular bond, you can identify something called the bond order, which means how many pairs of electrons are being shared. The bond order is related to 2 measurable quantities, the bond length and the bond energy. You should know their definitions and how they're related to each other. We found that sometimes the Lewis structure we draw that obeys the octet rule doesn't match experimental bond lengths and bond energy data. So we have come up with a way to improve Lewis structures, and that is by calculating formal charges of atoms. So you need to be able to calculate formal charges. And we found that if atoms could exceed the octet rule, then by reducing their formal charges to 0, we wind up getting a Lewis structure that most closely resembles the true bonding in a particular molecule. And we've seen situations where you can actually draw more than one Lewis structure for a molecule, so that molecule possesses the property of resonance. And the correct Lewis representation is you drawing every resonant structure with double-headed arrows between them. Okay? Once we got good at that, we actually learned a theory called the VSEPR theory to predict molecular shapes. And I'm going to be asking you, when you draw Lewis structures for molecules, I'm going to say, what's the shape of the molecule? And in order to determine a molecular shape, you have to determine the steric number. The steric number tells you the orbital geometry. And then by you knowing how many lone pairs and bonded atoms there are, the molecular shape is determined just by where the atoms are in relationship to each other. And all these different molecular shapes you'll need to know are all found on handout 4. Okay. Then we talked about a property developed by Linus Pauling called electronegativity, which tells how much an atom tracks shared electrons towards itself. You need to know its trend on the periodic table. We use electronegativities to tell if bonds are sharing their electrons evenly or not. If 2 atoms, I should say atoms are sharing their electrons evenly when they bond. If 2 bonded atoms are sharing their electrons unevenly, they're going to be called polar covalent bonds. They have an electronegativity difference greater than 0. If 2 atoms share electrons perfectly evenly, that's called a nonpolar covalent bond. They would have the same electronegativities. That's why they're nonpolar. And we can use these to determine, and once we determine if bonds are polar or not with their electronegativities, if we know the shape of a molecule, we can draw dipole moment arrows along all the polar bonds in a molecule, see if any of them cancel out, and we can determine if the molecule is polar or not. So many molecules on the test, you'll draw Lewis structures, you'll draw the shapes, and you're going to answer whether they're polar or nonpolar. Now, the whole idea as to how atoms bond together is that they actually have atomic orbitals on 2 different atoms overlap, combined together to form molecular orbitals, which we call bonds. So that theory is called valence bond theory. And Linus Pauling was looking at that and going, wow, If oxygens and hydrogens are going to bond by overlapping their valence orbitals, how come a water molecule comes out 109 degrees angle instead of 90 degrees? And so he proposed that atoms, before they bond, undergo a process of hybridization, and you'll need to be able to predict the hybridization of atoms and molecules. And then I'm going to want you to try to draw the correct geometrical picture of a molecule showing all the orbitals and all the bonds. We call that a bond orbital model. And then when you do that, you always then include the names of all the bonds in the molecule. So naming the bonds would be included in that. On your activity 9 this week, you're going to be doing that for a large number of molecules. You actually already did it in some homework last night and the night before. So you'll see it again in homework 2R, but the major practice you're going to get is going to come from activity 9 that you're working on this week. Okay? Then at the very end now, we started talking about maybe a more powerful theory of bonding, which is more complex, and we couldn't apply it to molecules with more than 2 atoms, because in actuality, if you do, you need computer programs to generate how the molecular orbitals would be created. But we applied molecular orbital theory to really simple molecules, diatomic molecules, and it really bases itself on the fact that when atomic orbitals overlap, they can overlap with the same wave function sign or with different wave function signs. Therefore, 2 atomic orbitals always create 2 molecular orbitals. They'll create bonding molecular orbitals, which have most of their electron probability between the 2 nuclei. And they'll have anti-bonding molecular orbitals, which has an empty space of electron probability between the 2 nuclei, which is actually called a nodal plane. So molecular orbital theory predicts the existence of bonding and anti-bonding orbitals. These can either have perfect symmetry around the internuclear axis, in which they're called sigma molecular orbitals, or they can only be symmetrical upon a 180-degree rotation, so they're called pi molecular orbitals, and these are independent of each other. You can have a bonding that's pi or a bonding that's sigma. You can have an anti-bonding that's sigma or an anti-bonding that are pi, so if I give you pictures of orbitals, I'll expect you to tell me whether it's bonding, whether it's anti-bonding, whether it's sigma, whether it's pi, just by looking at it, okay? And then we learned that if you bond 2 atoms in either the first period of the periodic table together, or 2 atoms from the second period in the periodic table, we can predict all the molecular orbitals are going to be created. And if we draw an energy diagram of all those orbitals, that's called a molecular orbital energy level diagram. And by filling in all the electrons for the 2 bonding atoms, you can therefore predict with this theory now bond order. You can predict whether the molecule is going to be paramagnetic or diamagnetic. And then you can write out the electron configuration notation for all the valence electrons so we can exactly say where they are. And you'll see all these on homework for tomorrow. Finally, we only applied molecular orbital theory to larger atoms if the molecule possesses resonance. Because when something possesses resonance, what it must have is it must have on each of the atoms that can participate in a double bond in 1 or more resonance structures, those atoms all have to have p orbitals that are unhybridized in their outer shell, and they all have to be parallel to each other, so they all merge together to make big orbitals that encompass multiple atoms. And we call that a delocalized pi system. And we'll see that on the homework tomorrow. You'll see it on activity 9. You'll see it on homework 2R. You'll see it on test 2. Okay? Then today we learned how to do an empirical formula calculation. We'll see that works as you do those tonight. We learned how to calculate molar masses of compounds. And then we learned that if you have data to calculate the empirical formula and you know the molar mass of the compound, you can calculate its molecular formula. So that was from today. I'm sure you've read through the 2 chapters for this particular unit. The activities we've done are activities 6 and 9. Activity 6 was naming compounds and writing their formulas. And although I will not be testing you on that specifically on this particular exam, we did talk about the definitions of acids and bases for activity 9. So make sure you know those for activity 6 rather. And then activity 9, of course, this is everything that's going to be on the test: hybridizations, shapes, polarities, Lewis structures, and bond orbital models. So that's a big portion of the test. Experimental work, we did experiments 2, and we did 7A in person, then you did 7B and 13 online, and I will ask you questions from those experiments on the exam. So experiment 13 was on chromatography. Make sure you understood how that worked and how we determined what chemicals were in an unknown based upon a chromatography separation. We learned how if a colored substance appears in a particular mixture, that you can actually measure the amount of light absorbed, and by comparing known concentrations to your unknown, you can determine the amount of a colored species in a sample. So you'll have problems like that from experiment 7B. And then from experiment 7A, you'll have questions on how do you separate chemicals based upon their solubilities. And if you've done that this week already, or you're going to do it the next 2 days, you'll see that in experiment 7A, where we separate things by either filtration or by recrystallization. And that really involves you understanding solubility curves. And I will have a solubility curve on the exam, and I'm going to ask you questions about it. So the post-lab questions in 7A will be really relevant.